Yeah, be right back. I'm just going to get a massive computer to simulate billions of years of like heat transfer across the moon.
You're listening to The Cosmic Cast. Hello and welcome back to another episode of The Cosmic Cast. I'm John Panny-Fisher and I'm joined with the usual co-hosts of Marissa Lowe and Elliot Carter.
Hello.
And joining us once again for the second appearance is Dr. Josh Snape, who is now joining us in the Manchester family.
Hello. Yes, very happy to be joining you.
Well, it's good to have you indeed. So we've got you on today because very excitingly, you were part of some of the cool science that's been coming out of the moon very recently, where for those in the audience, I'm sure you're aware, there's been some new samples from the moon returned with the Chinese-led Chang'e 5 mission. And Josh, you very excitingly were part of that team that produced some of the first analyses from some of these samples. So I guess maybe first we could just start a bit about asking how you got involved with working with these newly returned lunar rocks in the first place.
Yeah, it's been a long time coming. I mean, as with any of these kind of missions, like, you know that there is sort of something in the works quite a way ahead of the actual mission happening. So everybody knew that these missions were planned, and there were the various precursor missions to Chang'e 5. And so with that in mind, back in, when did I start some of these collaborations? It would have been 2018, I think, when I was still in Stockholm, working with Martin Whitehouse and Sasha Nemchin. And they both have connections with SIMS labs in China, so two different SIMS labs. And so, in 2018, I went over with Martin and with Sasha, and we spent some time visiting both labs. And yeah, over the last couple of years have been building on these sort of collaborations, and particularly in the last maybe year and a half, sort of established I guess what's now referred to as our sort of Beijing. I'm going to get in trouble for not remembering the official name, but the Beijing I think it's the Beijing Planetary Science Center, or International Planetary Science Center. But so yeah, it's kind of just one of these things, one of these stories of sort of relationships with sort of supervisors and friends of friends. That sounds really bad. It sounds like an old boys network, which I guess it kind of is in a way. But yeah, and just making the most of talking to people and networking.
Yeah.
And it's ended up with this, which is what you want to happen, I guess.
Absolutely, that's very cool indeed. I guess sort of for context, I suppose, we look at the moon and we think of all the large mare basalts and all the large grey areas up in the sky. This is something very very far away from some of the Apollo sites, wasn't it?
It was, and it was, I guess, a kind of mixed blessings in a way with the selection of landing site, because there's a lot of people like myself who are intrigued about the earliest stages of lunar evolution, and who are kind of really chomping at the bit to get samples from the far side of the moon, in particular from the parts of the South Pole Aitken Basin, where we may get hints of like very early volcanic activity. And so I wouldn't say disappointment, but you're always weighing up the pros and cons of like the different sort of scientific payback of different landing site selections. And it was very obvious from the choice with the Chang'e 5 mission of landing site that the amount that we were going to learn about the sort of early magmatic evolution of the moon was probably going to be fairly limited, and it was going to be much more telling us about the young evolution of the moon based on what we know from sort of crater counting studies of sort of volcanic flows in that area. Everything that we see there seems to be very young. So yeah, in that sense, it's really neat, because it's telling us a different story from the kind of the early moon evolution. It's telling us about how long that volcanic activity went on, and it's also giving us a chance to better calibrate these kind of crater counting sort of crater density models that we use for getting the ages of planetary surfaces where we don't have samples.
So yeah, I was reading different articles about the mission, and I saw that they'd collected about 1.5 or 2 kilos of rock.
Yeah,
what's happened to all of that, and how much did you get to work with?
So I mean, it's, I guess, a similar kind of model in a sense to the way that the Apollo and the Soviet lunar samples were distributed, and they've been they're being hosted in a sample curation facility in China, and different groups are applying for allocations of those samples. I can't actually remember what the total mass was of the allocation that we got, but for the paper that we're talking about here, we're talking about 2 tiny little basalt chips that were like a couple of, well, probably about 1/2 centimeter across each. So really not very big samples. And that's the kind of beauty of the modern sort of analytical approaches that we use, is that you don't need much to get these numbers out of them. So yeah, there's still a lot to be analyzed, and one of the things that's going to be interesting going forward is, as different groups apply for sort of new allocations of samples, is seeing whether there's any variation in the different sort of aliquots, I guess, of the sample material, whether we start seeing signs of different basaltic units or different sort of impact derived lithologies, for example. So it's something that we're working on ourselves, because there are more samples within the allocation that our group got, and I'm sure that other groups are kind of frantically working on it as well.
But I guess the headline here, which I don't think we've sort of explicitly stated then, is that, you know, what you and your group have dated then is some of the youngest basalts that we have so far from the moon. Yeah, so going into this, we were kind of looking at the predictions for the sort of the basaltic units in the area where in the landing site area. Sorry, I'm forgetting my words. But basically all of those predictions come out with ages of around 2 billion years, depending on which particular study you look at and which particular cratering model you look at. It's kind of 1.5 to 2 billion years. So this, I mean, even there's a fairly big sort of error margin. Yeah. And the age that we got and the age that subsequently has come out from the other SIMS lab in Beijing has basically pinpointed that to the 2 billion year sort of area. So it's on the upper end of the predictions, the sort of older end of the predictions that were made for that area. I guess it's encouraging though that, you know, it's generally within the right ballpark, because I'm guessing a lot of these crater models, I mean, they're all, you know, constrained through all the Mare stuff that are, you know, 3+ billion years old, aren't they? So I imagine there's quite a large error when you start to extrapolate out to younger ages. Yeah, it's something that I've joked about with various colleagues, that like if I were somebody like Harry Hiesinger, who's basically built my entire career on these cratering models and generating sort of predicted ages, I would have been really, really nervous, I think. So yeah, I'm sure there's a sense in which it must be, well, I mean, I think for all of us, it's kind of nice to see that the model is working. Yeah. I guess the flip side, this sort of silver lining to if we were in a hypothetical parallel universe where it had gone the other way, is that we would have had interesting science questions to answer if it had not been what we expected. But it's a very diplomatic way of putting it. But yeah, I think everything makes sense. So that's reassuring. Yeah. Broadly, everything makes sense. There's still some new questions here. So we can get onto that later in terms of what's driving some of this late stage magnetism.
I guess, yeah, that was going to be my question. So what, I mean, to a lot of people, 2 billion years versus, you know, 4 odd billion years, they both sound very old. What is the significance of these quote unquote young basalts?
Yeah, I mean, as you point out, like the difference in ages, and it's a good thing to highlight. Like prior to this, our sample-based knowledge of lunar volcanic activity basically stops at about 3 billion years. There are, I mean, certainly as far as the Apollo record is concerned, that's I mean, I think Apollo 12 has the youngest basalts. They're about 3.15 billion years. You get some very old things that are coming out pretty much as soon as we think the magma ocean finished crystallizing, so about 4.35 billion years. But yeah, after about 3 billion years, it really seems like volcanic activity just kind of goes off a cliff and everything seems to get very stagnant. And yeah, I mean, I can understand that from the point of view of someone who doesn't think about these things very much, 2 versus 3 versus 4 billion years may not sound like much, but I mean, we're talking about big units of time, right? We're talking about billions of years. We're talking about large percentages of the moon and the entire solar system history in terms of these differences in time. And it opens up questions in terms of how you keep a small body like the moon volcanically active for that length of time, because most models would generally suggest that the moon is small enough that it would have kind of died volcanically by this point, and that there wouldn't be much kind of volcanic activity going on at 2 billion years. And prior to analyzing these samples, there had been suggestions for how you might sort of make this activity, or how you might explain this activity. Because I mean, when it comes to explaining volcanic activity, you need to do 2 things. I mean, you need to explain both the source of heat for melting the actual material that you're going to erupt, and then you need the actual mechanism for driving it. And both of those things are hard to do if the moon is kind of cold and dead inside. So yeah, I mean, one of the suggestions which have been very popular, especially given the location of these samples, is the idea that maybe you have increased amounts of sort of heat producing radiogenic elements in the source regions. And that's one of the interesting things that came out of our work, and has actually reassuringly been backed up by the following studies from the Academy of Sciences, is that there actually isn't as much sign of radiogenic elements in the sources of these basalts as we would have expected. And so the idea of them being kind of heated by sort of radioactive decay is actually seems to be potentially off the cards, and we need to think up of a different mechanism for generating that heat and driving that volcanic activity.
So how do you assess that? Like which heat producing elements you're looking at? Is it like aluminium or potassium?
So for us, we are at the moment sticking with the same isotope system that we use to date the rocks. So with our study, we were looking at the uranium lead system, and you look at the lead isotope compositions, and in particular, what we refer to as your initial lead composition. So this is essentially like a little kind of isotopic geochemical fingerprint for that volcanic rock that gets kind of frozen in time at the point at which it formed. And what we can tell from that, when you combine this initial lead composition with the age of the samples, you can tell the sort of ratio of uranium to lead that would have been in the source. And that's basically giving you a proxy for how much kind of radiogenic material is there. And what we see is that it's not drastically different from what we have at the other Apollo landing sites. You have the vast majority, like 99%, would be some fairly primitive kind of mafic cumulate. And then you might have maybe sort of one or probably not more than 2%, but probably more likely less than 1% of this kind of late stage creep material that you get at the end of magma ocean crystallization, which is, it's really not very much. It's much less than I think some people were expecting. And like I said, this interpretation has also been backed up with one of the other papers that came out of the Academy of Sciences, not looking at the lead isotopes, but looking at strontium and neodymium isotopes. And you can kind of, you apply a similar approach where you look for the initial isotopic composition of the sample. And again, these are little fingerprints, but for those respective isotope systems, and they tell the same story. They actually look very, very similar to the Apollo basalts. So it's, again, it's reassuring that the different methods are kind of in line with each other, but it does mean that we've got work to do. And I think now it's kind of over to the modelers. It's over to people like Marissa to tell us how this happened.
Yeah, be right back. I'm just going to get a massive computer to simulate billions of years of like heat transfer across the moon.
That's cool though, but I mean, it's still a very wide open question, I guess.
Yeah, I think so. And it's interesting when you read like the paper that our group published and the paper that I think it's the Lee et al. Group from the Academy of Sciences, in terms of trying to explain the sort of driving force behind this. Just completely different suggestions being made. It's very speculative at the moment. I mean, like I honestly don't know what the answer will be. From our group, we proposed a couple of different things. We suggested maybe the idea that maybe tidal effects could have a larger kind of heating effect than you might have previously modeled, sort of tidal forces between the Earth and the Moon and the Sun. I'm not 100% sure whether I buy that. I guess the other one that we suggested is whether you could just have a really unique mineral assemblage in the source material that would have a much lower melting point. Again, based on what I've seen so far, I don't know if that quite gets there or not. Equally, the other group was suggesting about having a kind of much larger insulating effect from the kind of crustal layer of the moon and really slowing down that cooling process of the lunar interior. Maybe that's the way to go. I honestly don't know. It's really, really exciting. Yeah. It's nice to be like in lunar science at this point when there's some new, really big unanswered questions.
Yeah, I feel like the story has been for so many years. Oh, about 3 billion years ago.
Yeah,
the moon was active.
Exactly.
Where does I know there's only a small handful of papers about very, very recent lunar volcanic activity with like irregular mare patches, so those strange surface features. Where do your results like change the story of that? Because I know not many people are convinced by irregular mare patches, because I think they were said to be around 100 million years old, which is crazy young in geology terms.
I mean, I don't think that will necessarily change the interpretation of that. So I'm possibly not the best informed to talk about those particular studies, but I'll give it a crack. As far as I'm aware, I mean, those predictions are still based on the same crater counting models, which essentially are still holding up in light of the new data that we've produced. And so as far as the ages that are predicted in some of those papers for very young volcanic activity, I think they would probably still stand. The question is whether it's more a separate question, I think, about whether or not you buy the interpretations of the remote sensing, the sort of other aspect of the remote sensing data interpretation from those papers, whether you really think that these flows are as young as they say. But from a modeling, from a crater chronology point of view, I don't think this has upset that at all. So I think that is also still open, and it's one of those things where we're certainly scouring through the samples that we've got, and I'm sure the other groups are, for anything that might be younger than 2 billion years. Because, I mean, we know that the lunar regolith is this very sort of heterogeneous thing that's just being constantly mixed over geologic time. And so it's perfectly possible that we may have samples of potentially younger material in the things that we've already collected, just that's been introduced by kind of lateral mixing from impacts. So we're keeping our eyes peeled, I guess.
Yeah.
Oh yeah, I suppose with all of these difficult questions, what more information would you want in order to answer these questions?
Yeah, I mean, it's actually myself and Roman Tartez who are part of the group now, looking at the additional basaltic samples that we've got. And so from our point of view, we're trying to go down a much more, I guess, a much more thorough sort of process of pulling these samples apart and analyzing the mineral chemistry, and really, I mean, when we first had the sample, there was a sort of a discussion about how we approach it and how do we best get a publication out as quickly as possible. And the answer from everybody was essentially, well, we look at what the top level science question is, and that is, how old are these samples? And so the whole focus became about dating the samples. And not to say that corners were cut, but definitely we massively accelerated that side of the project. And now it's a question of sort of sitting back and taking stock, and like I say, getting all the mineral chemistry, really nailing down the bulk compositions of these samples, trying to work out like what is similar and what's different about the different basaltic clasts, and seeing if we can fit them in with earlier models that were produced, for example, with the Apollo basalts. So, I mean, like back in the 90s, people like Snyder and Clive Neal and Larry Taylor did tons and tons of work looking at the modeling of the sources of the Apollo basalts and how you explain them. Now it's going to be our job to try and work out where the Chang'e 5 basalts fit in. So yeah, it goes way beyond just looking at the ages of them, and yeah, into trying to work out the sort of the kind of the nature of the sources from which they came from in a much more detailed way.
It's a really basic question. If you're looking at, say, just the bulk chemistry of one of these samples, how much gets used to do that? Because if I was looking at a coarse rock on Earth, I might homogenize like 2 kilos just to do one sample.
You've just kind of hit the nail on the head in terms of like one of the biggest issues that we have. Like, yeah, we're looking at tiny samples, and it is clearly the case with like some of them you look at and within a split second you can see the size of the sample overall is on the same order of magnitude as the grain size. And so there's like a massive red flag there in terms of whether or not what you're looking at is representative. And this is where it just becomes one of these slightly tedious games of statistics, and just getting more and more measurements of different samples and just driving it down. It gets back to work that I did during my PhD, looking at the mineral chemistries of these, where we were looking at tiny little soil fragments from Apollo 12 and trying to see if you can find some other way to approach the groupings of basalts other than bulk chemistry, because this is what's always been used for the Apollo basalts primarily. There is mineral chemistry data out there, but it's very limited, and there's never really been a successful attempt to kind of group things from a mineral chemistry point of view in a way that you might sort of get around this problem of representative chemistry. And I think that's very much still another open issue. In a sense, that's why the isotope systems are kind of helpful, because something like an initial lead composition or an initial strontium composition allows you to kind of sidestep that issue slightly, because you can access minerals where you know from a kind of sort of geochemical theory point of view, you know that they will be preserving that initial isotopic composition. But yeah, that's still, it doesn't help in terms of answering the question about the major element chemistry of the sources of these rocks. And yeah, it's a really, really big problem. And also, like, what you, not just in terms of what's representative of the parent rock from which the samples came from, but what's representative of the parent melt from which they came from, you know, like, so it's really tough, really, really tough.
Do they have like a lot of crystals? That what kind of size things are you looking at here when you're looking at crystal?
Quite variable. I mean, some things you see with almost kind of millimeter scale mafic phenocrysts, and then tiny sort of 10 to even submicron scale, like sort of porphyritic, even vitreous kind of matrices. But then the vast majority, I would say, are kind of somewhere in between that, where you get more aphytic and subaphytic textures, where you're looking at kind of hundreds of micron sized minerals. But it's still, I mean, like I say, I think in one of the original questions that you asked me was like how big the samples were that we were looking at, and they were not much more than a couple of millimeters. So when you're talking about hundreds of microns, it's already quite a scary kind of size of crystal grain for that, relative to that size of sample. So yeah, it's definitely just a question of as many analyses as possible, and just trying to get enough that you think you've got something that's statistically significant.
Yeah, I was going to ask, the moment when you worked out your final number of years or whatever, were you doubting yourself? Were you there like, I better type this in the calculator again, you know, better check my workings? What was that moment like?
Not so much. So that, I mean, that gets onto the nature of how we were processing the data as a group, because all of this was happening during pandemic lockdown across the world. So if you look at the author list of the paper that we were involved in, we've got people from the US, we've got people from the UK, from Europe, we've got people from China, people from Australia. And within that, there was myself, there was Martin Whitehouse, there were the people in China, and then there was Sasha Nemchin in Australia. And I think all of us were kind of separately playing with the numbers. And so that it wasn't so much, I guess it was more nerve-wracking checking each other's numbers against, like checking whether everybody had got the same number, you know, which we did. And then, like I say, the fact that the subsequent paper that came out with another lead isotope study and another age is also pretty well in agreement. There's a very slight discrepancy in the final age, but when you actually start really digging into the lead isotope systematics, it's basically in very good agreement.
Well, yeah, that's really reassuring. And also, it's been amazing to see the number of papers and how quickly they've all been coming out.
Oh yeah, I think, I mean, our group was working really frantically. In some ways, I think we almost benefited from the fact that we were working in different continents and different different time zones, because when half of us were asleep, the other half could be carrying on, like working on things. And so there was genuinely periods where like we like, it was a couple of weeks in particular in the summer where there was just going to sleep, waking up to a new draft of a paper, doing your own little edits, and then sending it, and then going back to sleep and waiting for the next draft in the morning. And I mean, in some ways it was kind of brutally efficient, I guess. It kind of worked. I can only imagine what it was probably like to be there in person in China, in both the Beijing shrimp lab that we were working with, but also the Academy of Sciences. I think it must have been frantic. Yeah, there's a part of me that was kind of glad I was shielded from that a little bit by distance. I think it would have been even more stressful.
Now things are opening up a bit. Are there opportunities for you to go out there and visit some of these labs?
Yeah, I think so. And I mean, that's one question, is about people going to China. The other big question is about samples, the samples coming out of China and going to other labs worldwide. And I think we're still at the early stages of that.
Yeah.
But yeah, hopefully that will become more possible, and that will obviously open up kind of avenues for different analytical approaches and really sort of getting more data out of these. But yeah, hopefully we're getting there. Although I mean, I know that just from the point of view of looking at these basaltic samples and getting even just something at what to us seems as simple as electron probe data, even that seems to be taking a long time. Like I know that they're currently having some new lockdown regulations, I think, which is stopping them getting to the lab they need to be. So yeah, we're still struggling a bit with this, but it's not too bad.
What was the timescale between, you know, them getting the chips of sample and published paper?
Oh, that's a good question. I would have to check my email trail. My memory is that I got a first SEM image of one of the samples, I think in June or July, and then
Wow,
within basically a month or two, we had all the SIMS data and the paper was submitted.
I mean,
it was really, really intense.
Yeah. To be first author of that paper, that must have been particularly stressful.
I think so. And you know what, that I need to probably give a kind of a special commendation to Chang'e, the lead author. He did such a fantastic job. He was getting conflicting information from different people when it came to like set up and sort of analytical protocols. Everyone who has their own, I mean, everyone's got their own like very strong opinions about these things, and there were definitely times where he would get one email and then 5 minutes later go, no, that's rubbish, you don't do it that way. He did a remarkable job. He's a very patient guy, and the first authorship is very well deserved. Yeah.
So I suppose, as an aside, is this the main project you're working on at the moment, or like have you just dropped everything else while all this excitement has been happening?
I mean, yeah, during the summer it did kind of take over everything, but no, it's not my main project. So now I'm trying to get back into essentially what my fellowship in Manchester is all about. So it's kind of building on work that I'd done previously in Amsterdam that I talked on the podcast before about. So this is a kind of combination of experimental techniques and sample analysis to basically build models for the early magmatic evolution of the moon. So looking particularly at things like partitioning of different parent-daughter pairs in different isotope systems, and extending that work. So I did some kind of first kind of preliminary studies, I guess, in Amsterdam, and I don't know, as is always the case, you never get as much done as you hope. So I'm kind of glad now to have an opportunity to build on that and basically do more experiments and analyze more samples and kind of push that further. So yeah.
That's pretty cool. It seems that experimentality has become really trendy at the moment. The sheer number of people that seem to be getting involved with it.
It's not my fault. I don't know what to say to that.
That's just.
I mean, it's a really it's a.
But it's a powerful tool, I guess.
Yeah, and it's also, there is something really satisfying, like after spending sort of the best part of a decade just analyzing samples and being completely at the mercy of the samples that you're able to get.
You're in complete control.
Yeah, when you do your first experiment, this realization of like, oh wow, like I can just make a new sample. That's really, really cool. I mean, it's not quite that, and as I've just from budgeting my own fellowship now and looking at how much these things cost, it's not quite that simple, and like each experiment costs a bit of money. So yeah, you can't be quite so flippant about just running tons and tons of experiments, but it is still fundamentally, it's a really neat thing, and it's very, very satisfying when you do a new experiment and you get your little experimental charge and you mount it up, and it's just neat how much they actually really often look quite a lot like rock samples, you know, and you're like, that's really neat. I do a little rock.
Yeah, one part of like experimental papers I do like seeing is all the SEM pictures they have, and all like the really nice textures they always seem to get and all that kind of stuff.
Cool. I had a whole bunch of really nasty ones in the like when I was first starting and just kind of trying to work out the right conditions. Some of the last experiments I did in Amsterdam, I was looking, I did a whole bunch looking particularly at ilmenite. I got some really, really nice sort of skeletal crystals, and they're beautiful, really lovely.
But yeah, so but bringing it back round to this new Chang'e 5 paper, then we'll pop a link in the episode description to the paper that you're a co-author on, and maybe some of the other papers as well that are out there that have been published so far, if anybody in the audience wants to read a bit more about this. But Josh, thanks very much for coming on to chat to us. Yeah, it's really interesting, and I'm sure once you've got some more results about all of this, we'll have you on again to chat more about this as this very exciting story unfolds.
Sounds good.
Yeah, absolutely. Well, yeah, thanks again, and we're sure we'll see you around in Manchester very soon. But in the meantime, to all of us watching, to all of you watching rather, thank you very much, and we'll see you all next week. Don't forget to like us across all the various social medias, on the Twitters and the Facebooks, etc. Links, episode description, and on screen now. Until next week, see you all very soon. Bye.
Bye.
Bye.